Okay, in today's class, we will discuss about this Wiener filter. We have already discussed about this random process and the random variables and the various statistical parameters that we estimate, like the expectation, the variance, the correlation, autocorrelation, cross correlation, what is a stationary process, what is White's unstationary process, okay, and then how the autocorrelation and this power spectral density they are related to each other, and so many other things, basic things. So Wiener filter is basically what is the problem statement in the Wiener filter. If you take a normal digital filter or analog filter, what we have in that, you give some input sequence to a device which is a filter, and this device gives you output which is called as a filtered sequence or the filtered signal. Okay, so if it is analog filter, you apply a input here xt and you get a output yt. So we say that yt is a filtered output. It means this device or this filter has eliminated some frequency components from the input signal. And similarly, if it is a discrete time sequence xn, correspondingly you have a discrete time or a digital filter, you will get a digital signal yn or a discrete time signal yn, which is a filtered sequence. Okay, and this filter, which is either analog or a digital filter, it is nothing but a system. We model it as a linear time invariant system, so which generates the output according to the frequency response of the system. Okay, so the normal filters, they are basically designed based on some frequency response criteria. Okay, so you may have a low pass filter. If you take ideal low pass filter like this, so if it is analog filter, so between 0 frequency up to some frequency, cutoff frequency omega c, the frequency response of the filter is unity. Okay, and beyond that it is 0. So this filter will simply pass all the frequencies which are within this band, which is called as a pass band, and it will stop the frequencies which are beyond omega c. Okay, so when we design a filter, the problem is to design a device system in such a way so that you can control its frequency response. So it is a frequency selective device. Okay, so based on the frequency response, where the frequency response is 1, so that frequency is passed as it is. Okay, where the frequency response drops to 0, so that frequency is basically stopped by the filter. Okay, this is what is a normal filtering operation. So you have only one path. Okay, you apply input to a device or a filter, the filter processes it and it generates a output signal or a output sequence depending upon how you have designed this filter, whether it is a low pass, band pass, high pass, notch filter, whatever it is. Okay, so mostly these kind of filters, they are designed based on some frequency response criteria. Okay, and this frequency response is decided based on the problem statement that you have, that which frequency band you want to pass or which frequency band you want to stop. So based on that, you have to first specify the frequency response, and based on this frequency response, then we design this filter either in the analog or in the discrete domain. Okay, this is what is a normal filter. Now when you have how Wiener filter is different from these normal filters, FIR or IR filters. So in the Wiener filter, the problem statement is somehow different. It is called as a optimum filter. Okay, linear optimum filter. We also call it as optimum filter. So So the problem in the Wiener filtering is that you have some input sequence, let us suppose un or xn, whatever you take, and you apply this sequence to a discrete time filter which has some filter coefficients w0, w1 and so on. So this discrete time system or this discrete filter will generate the output yn, and then we have a response which is called as desired response dn, or in fact we have one more sequence which is called as desired response, and then we compute the difference between the desired response and the output of this filter, which we call as a estimation error en, which is difference between dn and yn. Okay, this is the estimation error, and the problem in the Wiener filter is now to select these filter weights w0, w1, w2 and so on in such a way so that this estimation error should attain its minimum value in some statistical sense. Okay, so in some statistical sense means you have to minimize the error using some statistical parameters. Okay, so generally we use the mean square error for optimization. So if an, which is the difference between the desired response and the output of this filter, okay, so the problem statement now is this: to choose, or the solution of the Wiener filter is basically to select these filter values, coefficient values, so that this error or the mean square error is minimum. Okay, it means you have to find the value of the coefficients in such a way so that the desired response and the output of the filter, which is now the estimate of the desired response, they are almost same, so that you get the minimum value of the error. Okay, now there are two restrictions that we impose here. One is that we assume that this filter is a digital filter. Okay, so that it can be implemented using a hardware or a software as you wish. And the second response is that, and the second, we assume that this is a linear filter. Okay, so we impose two conditions on that: it is a discrete time or a digital filter, and the second, it is a linear filter. Because of that, your mathematical computations will be easy if you assume linearity in the filter. And the second, one more thing is that this choice of the filter, it can be either a finite impulse response or a infinite impulse response filter. Okay, so but most widely in the Wiener filters we take this filter, or we assume this filter to be a finite impulse response filter, because IR filters, they have some stability, there are some stability issues in the IR filters. Okay, that if the poles of the filter, they are not inside the unit circle, then this filter can turn to be unstable because of that. And that happens because in case of infinite impulse response filters, you have some feedback. Okay, and because of that feedback, sometimes there is an issue of stability. So FIR filters, they are always stable. So that is why we prefer that in the Wiener filter, this basic filter structure that we are using, it is a FIR filter, means a filter having a finite response. Okay, and another thing is that the cost function or the index of performance that we define here, so that we take as mean square error. So mean square error means it is the mod n square expectation of this. Okay, so we suppose denote this mean square error with a variable j. So j is the mean square error. Okay, and we already know now what is this mean square error, what is the meaning of this expectation, that we have already discussed. Or alternatively, I can write it as E of En into En conjugate. Okay, so this is my cost function or index of performance, you can say. So the problem is now we have to select these filter weights W0, W1, W2 and so on in such a way so that this cost function attain its minimum value. Okay, it means at that point when it attains minimum value, the output of the filter yn and the dn or yn will be very close approximation of the desired response. Okay, so the problem in Wiener filter is basically you have a desired response and then you have a filter input sequence which is given to a filter, and you have to choose the filter weights in such a way so that the output of the filter is a very close approximation of the desired response that you have. Okay, or you have to minimize the error in a statistical sense, that you have to minimize the mean square error. And the reason for this, why we take, although it is not necessary that you only optimize this mean square error, you can take higher you can say powers of En also, or you can just take absolute value of expectation of the absolute value of En. But why we prefer to use this mean square error as a cost function, because if you see the yn now, output of this filter is basically a function of these filter weights W0, W1, W2. Okay, and later on we will see that this dependence basically, or this mean square error, it is a second order dependence on the filter weights. Okay, so if it is a second order dependence on the filter weights, in that case you have a distinct or a unique minima that defines the design of this optimum filter. Means suppose if I just take two filter weights, let us suppose I have filter in which we have only two filter coefficients W0 and W1. Okay, and you apply some input sequence to this filter and it generates some output yn, and then you have some desired response with you, and what you are trying to do, we are trying to find out the filter weights or optimize these filter weights so that your desired response or the is equal to the estimated response, or yn, which is the estimation from this input sequence xn, it should be very close to your dn. It means your en, the error that you are computing, it should be minimized in the mean square sense. Okay, and when you find this j function, that is expectation of mod n square, or which is the mean square error. So if you plot it j with respect to W0, and now since I have only two weights W0 and W1, so this plot of j with respect to W0 and W1 will be a two-dimensional plot, two-dimensional surface. And since this mean square error is a quadratic function of the filter coefficients or second order dependence, so you will have something like this, maybe a plot like this. Okay, that okay, corresponding to this value of W0 and this value of W1, you have maybe some error point here on this surface. Okay, so for different values of W0 and W1 you have different error, but there is a particular point here now at which point you attain the minimum error, minimum mean square error. So this is my Wiener filter solution. Okay, so this is W1 and this is W0. So this is W optimum point, you can say. So using the Wiener filter we are basically trying to find this point, and since the mean square error is a quadratic function of the filter coefficients, there is a unique minima or distinct minima that you can simply find out now using the gradient operator. Okay, so what you have to do, since yn is a function of W0, it is a function of W1, accordingly your en or the mean square error j will also be a function of W0, W1 and W2, right? It means in order for this cost function to attain a minimum value, the gradient of this with respect to all the filter coefficients that must be set to 0. Okay, this is what we will derive in this, and we will see there is a condition which is called as principle of orthogonality, where you achieve the minimum value. Okay, so I have so my filter is now, I have an input sequence, I'm applying it to a filter, discrete time filter with some filter weights. I am getting output yn, and then I am finding the difference between a desired sequence and this output of the filter, which is error sequence dn minus yn, and yn, since it is a linear filter, so you can simply say that if u1 is the input sequence, so yn, the output of this filter, for a linear filter it is nothing but the convolution between the input sequence and the filter weights. So you can simply write equation of convolution like this: wk star u of n minus k, k from 0 to infinity. Okay, and we assume here that the filter is causal, so that the summation for k is only from 0 to infinity, not from minus to plus infinity. Okay, and we are taking wk conjugate here because we assume that in general this filter coefficients, they can be complex. So wk can be have a real part, suppose ak plus j bk. Okay, so if the filter coefficients are real, in that case that will be a special case of this complex filter coefficients. Okay, so this is my wk filter coefficients, this is the output of this filter, and then you find the response dn an, which is dn minus yn. So in place of yn, I can write it as wk star u of n minus k, k from 0 to infinity. This is error signal. Okay, estimated error. And then you have cost function j, which is the mean square error, so expectation of mod n square, or in you can also write it as en into en star. Okay, conjugate. Now since this j, the means this mean square error, it is a function of filter weights wk, or in generally function of this filter weights ak and bk. So for this function j to attain its minimum value, the derivative or the gradient of j with respect to wk should be 0. Okay, it means if you define a gradient operator del, which will be now del by del ak plus j del by del bk. Okay, so differentiation with respect to the real part and differentiation with respect to the complex part. Okay, so when you apply this operator on this function j, you will get basically a gradient vector, which I suppose say as now del j. Okay, so del j is a gradient vector. So you, in the one case, you differentiate it with respect to a0 and w0, which is a0 plus jb0. So we will have one function here, del upon del a0 j plus j del upon del b0 j. Okay, another element of this vector will be, again you have to differentiate this function with respect to a1 and b1, and del j upon del b1, and so on. So it is a gradient vector basically. Okay, and the point where the minimum value of this mean square error will lie, so at that point this entire gradient must be 0. Okay, so what you have to do, simply you have to find the gradient of this mean square error function and equate to 0. So that will give you a necessary condition for this mean square error to attain its minimum value. Okay, so if you apply this del j, so j is this function, so if you apply this gradient operator on this, what I will get is expectation. If you apply now differentiation of the gradient on this function j, which is the product of two functions here, a and a n star, so you have to first differentiate it with respect to ak, then with respect to bk. Okay, so if I first differentiate with respect to ak, this filter coefficient ak, since it is the product of two functions, I can write this as first function an into derivative of second function, then plus second function into derivative of first function. This is with respect to ak. Similarly with respect to bk, and j will be there, so first function into derivative of second, that is en star, and then plus second function en star into derivative of first function, that is an. Okay, so what we have to compute is now these gradients, these four gradients. Okay, so if you compute these four gradients, let us suppose I compute first this del by del ak en star. So what will be it? This is my function an. If you take an conjugate, if you take conjugate of an, you will get here dn conjugate minus summation of, it will become wk into u of n minus k star, right? This is an conjugate. So if you differentiate with respect to ak and wk itself, or you can write it as dn conjugate minus summation of wk can be written as ak plus j bk into u of n minus k star. Okay, so if you differentiate this function with respect to ak, so differentiation of dn is 0, it is a constant because it is a partial derivative now. Okay, again in this term j bk into u n minus k star, its differentiation will be 0. The only part that you will get is ak into u of n minus k star, and the differentiation of this with respect to ak will give you u of n minus k star along with this minus sign. Okay, so it will be minus u of n minus k star, right? Similarly, if you find this, so this we have computed. Similarly, this gradient, if you find del upon del ak en, so you have to differentiate now this function, error function. Again wk, in place of wk I can write now ak minus j bk because it is conjugate now. Okay, and when I differentiate this with respect to ak, so differentiation of dn is 0, bk u of n minus k is 0. What you will get only is the ak into u of n minus k, and minus sign is there. Okay, so it is minus u of n minus k. Similarly, if you differentiate with respect to bk en conjugate, this one, again differentiation of dn is 0. Now in this case ak part, the differentiation of this part which has ak, it will be 0, and differentiation with respect to bk, we will get j, and along with this minus sign minus j u of n minus k star. Okay, and similarly last is del upon del bk e of n. So if you differentiate now this error function e of n with respect to bk, dn differentiation is 0, ak part is 0, so this minus into minus, it will become plus, it will become j, and differentiation of bk u of n minus k with respect to bk will give you u of n minus k. Okay, so if you put these operators here, what you will get, e of n into del by del ak en star, it will be give minus u of n minus k star, then plus en star, the second derivative is minus u of n minus k, so this plus will become here minus, and you will get u of n minus k. Similarly, in the next you will get plus j e n into del upon del bk en star, which is this. So it is minus j into u of n minus k. So minus j into this plus, it will become minus j square, and minus j square will become plus 1. So I can write it as plus 1 here into en into u of n minus k star, and plus in the last term now it is del e n upon bk, which is this. So j here and j here, so j into j becomes j square, which is minus 1, so minus en star into u of n minus k. Okay, so en u of n minus k star and minus en u of n minus k star, these terms will get cancelled, and these two will be combined together. What you will get here, delta j, which is e of, it will become now minus 2, or 2 minus 2 you can take outside, minus 2 into u of n minus k into en star. This is my gradient. Okay, so simply you have to equate this gradient to 0 for attaining the minimum value of the function. So if I make this to 0, so what I will get, so del j is now minus 2e u of n minus k into en star. So for optimum design, for the minimum value of the mean square error, this function should be set to 0, or what you can say that it means e of u of n minus k into en star, this must be 0. Okay, so if en, let us suppose that e naught n is the estimation error when this gradient function attains the minimum mean square value, it means at that case your e of u n minus k into e naught n star, this is 0. Okay, so this is a very important principle which is called as the principle of orthogonality. Okay, what this statement says that the v1 is the input sequence and e naught n is the estimation error when the filter is optimum. Okay, it means in order to attain the minimum value of the mean square error, or when the filter attains the minimum value of the mean square error, at that point of time the input sequence and the estimation error, their correlation is 0. It means they are orthogonal to each other. Okay, because this is nothing but the correlation between the input sequence and the estimation error. So every sample of the input sequence is orthogonal to the estimation error when the filter is operating in the optimum sense. Okay, otherwise you can also state this property like this. If you take the expectation of yn and en, the correlation between the output and the error, okay, you can write this equation as e of yn can be written as summation of wk star u of n minus k, this is yn into en, okay, or you can alternately write it as summation of wk star into expected value of u of n minus k into en, okay, or you take here en star. Now as per the principle of orthogonality that we have just derived, this factor is 0, expectation of u of n minus k into e star n is 0. It means when the filter operates in the optimum sense, at that point your e of yn into e naught n star is also 0. So the principle of orthogonality can also be stated like this, okay. It means when the filter coefficients are selected in such a way so that the mean square error is minimum, at that point the output of the filter or the estimation of the desired response and the estimation error, they are orthogonal to each other, their correlation is 0, okay. So this is one way how you can find this optimum point in the Wiener filter where the mean square error will be minimum. We will next see that how you find the solution actually of this point, optimum point, using the properties of the input sequence, okay, or the correlation matrix of the input sequence and this desired response. You can find a point which gives you the minimum value, which is called as Wiener filter solution, or those equations are basically called as Wiener-Hof equations, okay. So but right now what we have seen this is that for this Wiener filter to be optimum, so let me repeat it, that you have an input sequence applied to some filter, discrete time digital filter, linear filter, which generates a output yn using a linear combination of the input sequence with the filter weights, and then you have a desired response here dn. So the problem in the Wiener filter was to find these weights, or to find a set of these weights so that the mean square error is minimized, okay. It means this output yn will be very close approximation of this desired response, okay. And you will see that this filter is widely or practically used in many situations. When we will further discuss that, when we will go ahead, we will see that how Wiener filters, they are basically then converted to adaptive filters, okay. So in the adaptive filters, your filter weights, they are not fixed, they are adaptively changed in a recursive fashion, so that at every point of time you are going to minimize the mean square error. We are going to adjust the weights in such a way so that at every sample the mean square error is going to be minimized, and finally you find a point where the mean square error will be minimum, okay. So in that case your en error signal is somehow feedback to this Wiener filter. So we have a weight adjustment mechanism there, which we will discuss when we will study this method of steepest descent and this LMS algorithm, okay. But before that, we will find, right now we have not found the solution for the Wiener filter. We have just find a principle, derived a principle of orthogonality, or a condition for this filter to be optimum, that the estimated response yn and the estimation error, they are orthogonal to each other at the point when the filter operates in the optimum sense, or when the mean square error is minimum, okay.